Hi. Today we're going to start our bonding unit, so I'm just going to get right into it. We've talked before about atomic structure and some periodic trends, but really when it comes down to bonding, we should probably first talk about simplifying some of what we've already represented, because the periodic table gives you a lot of information and we might not need all of that. This here is an atom of barium. You can see that the protons and neutrons are given for the most stable isotope, or not the most stable, sorry, the most common isotope, 137 AMU. And the electron configuration of 28, 18, 18, 8, 2 is being shown. That's a lot of electrons. And when it comes to atoms bonding, coming together to make compounds, typically this amount of information is actually too much. And so we need to, we want to try and focus this down, distill it, if you will, to some of the most salient information that you only really need to communicate in order to move forward in talking about how this works. So I've also copied another element here. This is a magnesium. It's in the same group as barium, also shown. And don't forget that the reason they're in the same group, or I guess a product of the fact that they're in the same group, is that the valence electron number is the same. Remember that magnesium is 282, and barium is 2, I just said, 8, 18, 18, 8, 2. And it's that valence shell that really ties them together as being present in the same group. That valence shell, we also said that they behave chemically similarly, as in they'll make formulas with certain other elements in the same ratio as each other. So really when it comes down to it, the most important things I guess I would need to know are the number of valence electrons and which element it is. And that's really what we do moving forward in terms of bonding. We call them Lewis dot structures or Lewis structures, or electron dot structures sometimes, but it subdivides your what you would consider a Bohr atom into three components, well actually two components, the kernel and the valence electrons. We're going to represent the kernel with just the chemical symbol. So we've got, I'm going to draw our magnesium atom with our electrons all 282, but really we're mostly concerned with just the valence electrons, and then we're going to represent the entire kernel, which is the first, second energy levels and the whole nucleus, with just the chemical symbol of Mg. So we now need to know, oh yeah, magnesium, yes there's inner electrons, yes there's a nucleus, yes there's protons and neutrons, but we're really just mostly concerned with the two valence electrons, and we're going to represent them with dots, hence Lewis dot structures. Similarly, we want to do this with barium, except now we're going to represent all of those inner electrons, that 2, 8, 18, 18, 8, 2. All of this will now be represented, and the nucleus, by just writing Ba. So in a way, this is really, really nice because of how much it simplifies the process, but in a way it also is going to pull back on how much information you are communicating and is communicated to you that you have to kind of remember is hiding behind the scenes. You might notice that I put the two dots on the top of magnesium. And just to make sure we're all on the same page, I want to share a convention of putting these electrons in place. What I like to do is I always put the first and the second dot on the top, and then I would put the third on the side, and then I go and I have single electrons, 3, 4, 5. The sixth electron I end up pairing up with the third, and the seventh with the fourth, and the eighth with the fifth. So what we end up getting is, if you have one valence electron, it might look like that. 2 would look like this. 3 valence electrons would look like that. If you had an atom that had 5 valence electrons, you'd see this. And in this way, we're subdividing the electrons of the valence shell into 4 regions of 2 electrons each, top, bottom, left, and right. And if you have seen any sort of information about subshells and orbitals and how the electrons are filling in, you'll see that we do, as a convention, pair up the first 2 electrons, and that has to do with the s subshell, and then you've got your 3 p orbitals shown there. And of course, Hund's rule says why you're doing unpaired before pairing. In this way, whenever you have 1, 2, 3, 5, however many, up to 8 valence electrons, you will always see the same arrangement and the same number of paired and unpaired. So from here on out, we are going to throw a lot of focus towards the idea of pairing up electrons. They do tend to pair up in these orbitals. Each orbital can hold up to 2. So we have empty, 1 and 2 as our only options for electrons. And you'll notice that I stopped at 8, and you might be wondering, like, wait a second, I thought some of the larger electron shells hold way more than 18 electrons. True, but if you look at the periodic table, with very, very few exceptions, every single element as the last number in their Bohr configuration has a number that's 8 or smaller. So this works, other than those very rare cases, and in which case, the Lewis structure is a little bit weaker than we want it to be, but the condensed nature of it far outweighs any sort of drawback with those few exceptions. So going back to these 4 examples that we have here, I'm going to quickly just copy over the element symbols so that we can look at the Lewis dot structures. Right, so filling in our electrons, rubidium has 1 as its valence electron. Cesium also has 1. Strontium has 2 valence electrons. And barium has 2. So something we can already see is that within a group, it looks like the Lewis structures are the same. Element symbols are of course different, but the electron arrangement is the same, and that's in agreement with what we saw with the periodic table unit, and how like the valence electrons are the same, the chemical properties are very similar, and then the Lewis dot structures will be near identical, where you're just switching out the symbol. So now all of the group 2 elements, I mean, we could write one for any of the group 2 elements, and they would all look the same, except different letters, but the same dot arrangement. And then when going across the periods, you'll see that there is a difference, but now we're not really worried about the number of shells. So, of course, ionization energy, electronegativity, atomic radius, these are all still very important. But for now, we're going to kind of put those in the back seat, file them away in the back of our heads, and say we'll pull them out when we need them. This is a quick way of just representing the most important, the valence shell, the most outermost electrons, the electrons that do the most interacting with other atoms on a piece of paper. Thanks for watching.